The motivation for this work is that while learning has enabled tremendous advances in autonomy, as deployments scale, eventually a robot will encounter out-of-distribution inputs such as these real-world edge cases of self-driving vehicles. These edge cases, like stopping for a stop sign on a billboard, are really system-level reasoning failures. Our insight has been to leverage the common-sense reasoning capabilities of LLMs to handle such cases. But how can we practically increase closed-loop robot trustworthiness with LLMs? Doing so requires solving two key challenges. The first is to mitigate the computational costs of LLMs to enable real-time reactivity. The best LLMs are very large, and this makes them very slow. And that besides detecting anomalies, we now also need to integrate LLM-based reasoners into the control of dynamic, agile robots. We propose a two-stage decision-making framework to address these challenges. We first assume we have a data set of prior experiences of the robot where we assume it was reliable. We use a foundation model to generate a database of semantic embedding vectors. Then, at runtime, we take the current observation of the robot and compare its similarity with the embeddings in the vector database to detect anomalies. If the current observation is similar to previous experiences, we continue with the decisions made by the base autonomy stack. If the observation is anomalous, we query the second stage. A large model carefully reasons about what safety-preserving interventions to take slowly. The LLM chooses a fallback from a number of recovery sets, each corresponding to a high-level safety intervention. For example, for a drone delivery service, these sets may correspond to, say, landing in a field or hovering in a holding zone. We use the recovery sets within an MPC that maintains a tree of fallbacks associated with the nominal goal and a set of safety interventions. We compute embeddings of the observations in parallel to the MPC to detect anomalies. And we show that this can be done in real time. Then we provide the current fallback options to the LLM reasoner, and as shown in orange, we note that the fallback trajectories are constrained to overlap for an upper bound on the time it takes the LLM to return a decision, a consensus constraint. This ensures that the fallback options we provide to the LLM are still dynamically feasible once the LLM returns a decision, thereby allowing the MPC to safely enact the LLM's choice. This controller design also allows us to prove that our controller reaches the recovery set chosen by the LLM. As a case study, let's re-examine the stop sign on billboard example. The base autonomy stack detects the billboard on the stop sign and slams on the brakes on the highway on-ramp, which is not very safe. If we look at our approach, we see the vehicle first drives normally, but fires off a query to the LLM encoding the current observation once an anomaly gets detected. We note that an embedding-based similarity query only requires a single forward pass through a transformer, and therefore it's real-time feasible. We can run this approach at 20 Hz on an NVIDIA Jetson. Moreover, we can actually outperform a much larger model like GPT-4 at anomaly detection at a much lower computational cost. The planner then slows the car down while waiting for the LLM to return an output. Once the LLM returns its output, the car then takes a decision to keep driving. While we can detect anomalies quickly with small models, we see that it is in fact necessary to reason about the downstream consequence of an anomaly with larger models. We also run quadrotor evaluations where the nominal goal of the quadrotor is to land on the red box in the presence of a clutter of inconsequential objects. And we see that if we place a bunch of quadrotors on the boxes, the drone correctly detects this and goes to the holding zone instead. What's interesting about this case is that the quadrotors were seen in the nominal data on the ground, but they are detected as anomalies when their semantics change when they are placed on boxes. Similarly, if we place a previously unseen object on the ground, in this case a keyboard, we see that the anomaly detector flags this. The drone slows down while waiting for the LLM to output, whereas the drone immediately backs out of the landing when it detects the other quadrotor on the box. In the case of the keyboard, the drone confidently proceeds to land on the box, whereas the drone on the red box forces the LLM to output landing on the blue box. In our evaluations, the following key takeaways consistently hold. First, that grounding an anomaly detector in prior experiences via embeddings outperforms generative reasoning. That smaller models can do just as well as larger models at anomaly detection. That embedding-based anomaly detectors really only detect differences with respect to the robot's prior experiences, and that zero-shot chain-of-thought reasoning with large models is necessary to reason about the safety criticality of out-of-distribution scenarios. This shows that the fast and slow reasoners in our framework are both necessary. The fast reasoner enables reactivity, running about 357 times faster than GPT-4 on an NVIDIA Jetson, whereas the slow reasoner is really required for zero-shot out-of-distribution reasoning. Please see